Hi, welcome to another video. This is really part 2 of the previous video where I looked at bytes versus time. If you haven't seen the previous video, I suggest you go and look at it, otherwise you won't understand what's going on today. And in the previous video you could see I was messing about with bytes, adding different functions, adding bytes and taking bytes away, making them global versus local, and I didn't understand why there was a big difference. So I'll take this opportunity to thank Midas. He's obviously clued up with programming and assembly, so when he sees people like me struggling with C, he knows exactly what's going on. So thank you, Midas, for your input. This right number function is now available for this SSD1327 screen controller, the ST7735S controller, the ILI9341 controller, and I've already developed this right number function for the SSD1963 that I've got to get round to making a video and showing you guys. So this video is going to be my final code, what I'm doing to create these numbers. Just numbers, because if you have text, usually the text is not updated. However, if you want a number on the screen, like if you're reading a fast ADC, or you're making a voltmeter, something like that, you want a fast response for the numbers. You write the numbers, then go and have a look at your ADC, pressure sensor or humidity sensor. You do not want to be waiting for the numbers to be written to the display memory. This is my while one, the bit you saw at the beginning of this video, and I've taken out the spaces, but this is the sum of the right number 0. So I've just got a high nibble and a low nibble, looking at the first byte, then looking at the second byte, shifting it right, just so I've got a 1 or a nothing. Then that low and high nibble are shared and used again throughout the process, and you can see I write the data, the high and low nibble there, there, and there. I'm dividing the 8 bits for 8 pixels down to 4 bits per pixel. The size, it's only showing 4 because that's all I've got in the while one. If you're not utilizing them, they don't get built and compiled. They are 638 bytes and just under. Every time you're setting a pixel on the screen and the address has to increment, it's jumping up to this set display number font. So you can see, just to set the display memory, 70 bytes. Can't make it any smaller than that. But that's got to be really quick. The other evening, when I shut the debug down, I hit a cross up here on the right, and they disappeared off the screen. And could I get them back? No. So what I've established, I can now go up here to the middle, go to debug, and these buttons that look like they're greyed out and don't do anything, do actually do stuff. I can now set the layout to my debug screen, so the watch values and watch clock come up. Start debugger, same as before, just step over everything. Well, I don't think I've altered much, so this 0 had previously been 13.61 milliseconds. So let's step over it. Well, yeah, 13.74, so something's changed. Number 1, step over that. Oh, 13.6, so there's some difference there, I don't know what, but 13.7, 13.6, and that's where I left you the other night. So this is the function you've just been watching. The static char for the J, counting through the font, and then the high nibble and low nibble. Let me comment out all these numbers. If I go up to my newer functions, which is just under the space somewhere, well, here we are. So uncomment these. So the quickest way to get to that number 9 and uncomment the number 9, build. There we are. Get rid of that. Back up to 0. This was my new routine for each function. So I added all these extra nibbles up here, and now you can see each nibble exclusively represents a pixel. So high nibble 1 is that first pixel in the byte array I showed you the other evening. The low nibble is pixel 2, high nibble 2 is pixel 3, low nibble 2 is pixel 4, high nibble 3, pixel 5, so on and so forth. That's all I really did. And now, learning from Midas, this if may only take 1 or 2 clock cycles. It's faster than, say, picking out bits and then multiplying them. Multiplication and division take more clock cycles than, say, a simple if. So that's when I was putting like high nibble times high and low nibble times low. My function looked short and it took up a low amount of space in the ROM, but the whole function took longer to complete. And as I say, as Midas has explained to me, different functions take different amount of times. So this is my new routine for the 0. 8 nibbles, 8 defined addresses for each pixel. So 8 pixels in the font array. This is just the first number. And then 4 bytes out. So if I build this, first of all, let's see the stats. We've gone from 600 down to 486 bytes. So by adding bytes, we've made the function shorter. Although I've added some bytes, bytes are not being shared. There's no division within the function. What's important is the time. Start debug. So same as before, step over everything. Right, clear screen. You can see that's taken, what's that, 4 or 5 seconds? Yeah, the whole function takes 86 milliseconds, but it's taken about 5 seconds to complete. Wait until you start debugging a 32-bit microcontroller with a massive screen. You are there for half an hour waiting for it to do something. Right, so this is now my new 0. New 1, new 0, new 1, 2, 3, and 4. This value here is the previous function. So, right, let's step over my new 0. 9.13 milliseconds. By adding bytes, making sure I've got no divisions, multiplications, it's made the function very fast. And reduced the function size by over 100 bytes. I don't think I can make that any better. 9.13 milliseconds. So, step over the number 1. 9.18, 9.13. Right, this is going to step over the number 2, 9.24. In case you're wondering why different numbers take different amount of time, is because the bytes in the array, the font array, are in different places. So the JJ numbers change. So if I finish stepping through this, number 4, 9.2 milliseconds. So I'm really happy. That's with an 8-bit microcontroller running at 8 megs with a massive font, as you saw on that screen. But I could obviously speed up the clock, but it's all relative. Relative to what I was doing the other night, this is an improvement. I want to make each function fast. Doesn't matter what clock speed you're running. It's got to be fast, whether you're on a slow clock or a fast clock. And I've seen, by messing about with the code, you can make big improvements. So you might think, well, so I'm changing this font from 9.2 milliseconds from 13, 14 milliseconds. What difference does that really make? Well, if you're looking at an ADC and you've got a voltmeter, for example, and you're spelling out 4 or 5 characters, that makes a big difference, displaying 4 or 5 characters every tenth of a second or so. The last thing you want to be doing is waiting for a number to be displayed on the memory before you can go and look at the ADC again. No point having a fast ADC if it takes forever to get the number down on the screen. I'll show you on the screen. I'll use my old font that took 14 milliseconds. And let's see how fast it can count in 60 seconds. Then I'll show you my new font. Right, so I'll start with the original right number routine where each character took approximately 13.6 milliseconds. See if I can start this at the right time. Right, so nothing's going to stop here, so we got to watch at 60 seconds. So 1100 and we'll call it 1200. Right, this is now programming with my later new improved bright number routine that shaves 4 milliseconds off each character. Nearly there. So 1550 odd. 1550. Right, so you saw, it's only an approximation, gives you an idea. You saw the microcontroller was able to count an additional 350 times. Bearing in mind each character takes roughly 10 milliseconds. So if we can do that 350 times in 60 seconds, so 350 divided by 60 seconds equals 5.8 times a second. So your microcontroller, if it's measuring like pressure, humidity, temperature, any analog to digital converter, can be doing anything. It can be doing anything else. If it takes 10 milliseconds approximately, it can go and do that nearly 6 times a second. That's why it's important to have a fast right number routine. Yeah, the last thing you want to worry about numbers, isn't it? I tested this function. This was the most compact zero I could get, and this, like all my colour TFT functions, right number functions, it uses this I equals I, shifted left one place. So that's effectively multiplying by 2 every time it moves left, or to simplify it for the beginners, you're literally moving from bit 0 up to bit 1, bit 2 and up to bit 7. And on all my colour screens I use this, and if we have a look you can see it's all nice and compact. It literally starts at bit 1 and shifts up to bit 7, so that's 8 places. So within every byte I've got this for loop, x equals 0, x is less than 8, x plus plus. Couldn't get easier than that. Let me show you the size of this. So build, stats, there we go. So right 0, there we are, 318 bytes from 478. I thought, great, wouldn't it be fantastic if I could use this? But, as Midas has explained, different binary arithmetic operators take different amounts of clock cycles. So we've got to look at this. I demonstrated a short code the other night, and it took much longer than the routines you've just seen. So 318 bytes versus 478. Still got just the 2 nibbles. Right, step through, step over, rather, step over. It's ready to step over the right 0, so I'll clear this. So we're on a 0 count. I'll reset everything. Step over that nice compact 0 that uses that shift left, which is a multiply by 2. Step over. 35.2 milliseconds, which is still nice, but not compared to 13, and then the newer improved 9.6, 9.7. Yeah, it's really compact. What a shame. I can still look at stats. That's still available when I'm in debug mode. So 0, 318 bytes. The other function takes 10 milliseconds. This is taking 35.2. What a shame. So if I finish up here, so step over the 1, 9.18. Step over the 1, step over the 0, 35.2, but notice it took a couple of seconds just to give us that result. As I say, this debug tool is handy, but if you've got long codes, you go and make some dinner and a coffee or few. Right, so I'm on the number 1 and about to step over it. 9 milliseconds. I'm on the number 2, step over. Number 3, step over. Number 4. And that's the end. What I will do, close all. I'll open the Honeywell pressure sensor. Right, I've already got it set up. This Honeywell pressure sensor is obviously the same screen. I'll show you. The previous project did not use MikroElektronika's library. This one does. Look, TFT set, or TFT init custom, 128 by 128. And here's the identical font, so San Diego 20 by 27. This Honeywell pressure sensor project, I've now deleted everything but the TFT set font, San Diego 27 white, long to string, TFT write text, string, X++. So if I'll comment out the X for a minute. Let's build and program this. So this is the identical chip, identical display. I'm not swapping any hardware, just the software going to it. As I say, this Honeywell included MikroElektronika's library. Right, that's now shown a big 0 on the screen. It does not separate 8 bits into 4 bits per pixel, so it's writing 8 bits. 8 bits are 8 pixels. So each font is twice as wide as it should be. Other than that, there is no difference. There's no difference in timing. Nothing has changed. All this, here's the index which I had to set up for that display. It's still my same display. I initialized the display. So there's the index, there's a command, and where it writes the data, you've still got the same data port. I'm not swapping any hardware, I'm just swapping software. Same read, same write, everything. Everything is the same. Bytes being written to the display are the same. To display a number on the screen, using MikroElektronika's IDE, you have to set the font, San Diego 20 by 27, white, horizontal. You have to convert it to a string, which my function does anyway. And then there's the right string there. Let's debug this. Right, so as I said, I'm a novice or a hobbyist. You could say a hobbyist with a fair bit of experience programming, but I'm by no means an expert. I still rely on others, people like Midas, to teach me what I don't know. I expect MikroElektronika to be the experts, since they build this compiler and IDE and they sell it to the general public. Yeah, who am I? I'm just a hobbyist. Right, step over. Well, so I'm still on, as you can see, 8 megs. Step over this, milliseconds, 100 milliseconds. Right, look, to SPI init advanced. Let's see how long that takes to set up. 440 microseconds. That's not bad. Right, 10 millisecond delay. Step over. 10 milliseconds. Initialize the timer, because there's a timer on this. 5.5 microseconds. Right, here we are. TFT full screen black. Does the same as my clear screen, but it just uses different words to do exactly the same thing. I've touched nothing in the hardware or software. Nothing. So step over this TFT full screen. Mine takes 90 milliseconds. Step over. Are you watching your clock? Not this clock on the screen, your watch. Or clock on the wall. Hello, has it gone wrong? No, it's still counting. There we are, it's finished. 378 milliseconds. But that took like, what, 10, 12 seconds? I'll have to watch the video back and count it. 378 milliseconds to do what my function does in 90. Right, step over this current value. Right, set the font white. 58 microseconds, very fast. Long to string. 1.3 milliseconds, okay. This is it. TFT write text, so it's going to write that string to the screen. And nothing else. And that X has been defined as number 1, I believe. Can I scroll up without messing up the blue line? Right, here we are. Unsigned int X equals 0. Right. It's the same as mine then. That is going to write a 0 to the screen. Bear in mind these are professionals. I'm only a hobbyist. Step over. Hello. 69 milliseconds to write that 0. And I have got a 0 on my screen. Hang on. 69. That's 7 times longer. 7 times longer than my function. Let me run through it again. Maybe something went wrong. Right, long to string. 1.37 milliseconds. I didn't show you mine, but we'll go back and have a look. I chose a long because that's what my function does. Don't want to give anyone an unfair advantage. It's going to write that number 0 again. Only once. 69.53 milliseconds. And that, my YouTube friends, is the ugly truth to MikroElektronika's IDE. Are you thinking? Because I certainly am. I tried to, you can see I wrote here on the screen, write char. So it's just a 0, calling that 0 directly, and for some reason the debug won't even go into it. So I was under the illusion MikroElektronika were the experts. I mean, I do not know how to build a compiler. I do not know how to convert C into programming language for the chip. But one thing I do know is I should not be able to write code that's nearly 7 times faster than the suppliers of this IDE and compiler. That's ridiculous. This section of the video is actually many hours later than that just 30 seconds ago because my son called. So what you mustn't forget is, so we have all for, well, some of you maybe decades, but for me for the last, I don't know, 7, 8, 9 years, have had to write a number to a screen, a colour screen, and then blank it, and then write it again. In 2021, as I said the other week, that's just ridiculous. So don't forget this, write the string to the screen, took 7 times longer than my function, but then you've got to take this text, make it the same as the background colour, which means you've got to keep this function in your while one, and then write the string again in the background colour. So that's 67 milliseconds. I forget what it is now because it's so many hours ago. That 67 milliseconds is actually more than doubled. So let me do that now. Copy. So write string. Even on an OLED display, you still have to write it in black, even though there's only one colour for the pixel. I don't think I need to convert the string again. So just take this string, copy, paste. And in case some of you are wondering, oh, I'm converting an int and then using a long to convert it to a string, let's do, in fact, the easiest thing to do, because my function does use a long to string, which regrettably only counts up to sort of 4.5 billion. So if you want any numbers bigger than that, you'll have to use MikroElektronika's library, because mine won't cut it. Right, so back up to this unsigned int. So unsigned long, just in case. So build. Right, so I've built that. Right, so now we're down to the nitty gritty again. So set the font in white. 58 microseconds, anyone can live with that. Convert the long, which is now a long, to a string. 1.37 milliseconds. Write the string. There you go, 69.53. Is that exactly what we had before? It's so many hours ago, I forget. Right, now write it in a background color. So that's another 57 microseconds. We can live with that. 57 thousandths of a second. And write the number again. It should take the same time. 69.53 milliseconds. So MikroElektronika's IDE and compiler is not only super slow, you have to do it twice. I think having to write a character, I've moaned before, and I'm going to moan again, having to write a character twice in 2021 is just plain stupid in anyone's language. But then when we investigate how long it takes, it's taking nearly 7 times as long to write a character, 7 times as long as a bit of code that a hobbyist can write. What the hell's going on? Because as I've demonstrated here, it will not perform. Find a hobbyist on the street and he'll write superior code. And a final kick in the teeth for you, you may just, you're not knowing, you will add the TFT library, thinking, right, you want some TFT functions. Let me show you what that does. Right, so I've got my own custom display and I wanted the TFT library just to write one number. Right, SSD 1963 I or 1 or something. Right, what's that doing there? Right, TFT write char 624 bytes. PPS mapping. Right, ignore that. TFT write char E 1000 bytes. That's to obviously get something on the screen. This is 6 times smaller than mine. I'll show you in a minute. So set address of some display we're not using. Set the address of another display. Initialize the display 310. SPI long to string 264. TFT dot. Don't want a TFT dot. Long to string 234. 232. A long word to string. Fill screen 214 bytes. TFT set address ILI9481. I'm not using that screen. 200 bytes. Another set address 200 bytes. Set font 200 bytes. Hello, I recognise that display number. I'm not using it today though. SST7715R 200 bytes. Another screen 200 bytes. TFT get header, custom init, write text, 146 bytes. So some of their code you will see is a lot shorter than mine. But boy, none of it performs. Well, so just before I run through this write number function, I haven't showed you before, it will shock some of you. I've uncommented everything, so it's now capable of writing up to 999,999,999. That is why it's so big. If you only want numbers, say up to an integer, just literally comment out some of the functions and it will reduce this size. But I want to leave it capable of counting up to that just one position in a string short of a long which is nearly 4.5 billion, because I want to demonstrate how this slows my number down. So they're the numbers 0, 5, 8, 3, 4, blah, blah, blah. They're all just under 500 bytes. Long to strings. The only library I'm using on MikroElektronika's is this long word to string. But I bought this IDE, so I'm entitled to use a long to string. Unlike your compiler, I haven't got a load of garbage pertaining to other displays that I am not using. So if you add up all the garbage that you're not using, that's going to be 1,000 or 2,000 bytes easily. Generally, if you've got a display, you're looking at some sort of data, hence 10 numbers, 0 to 9, plus a space, and then my right number function. If you want text, text is generally static. So my right number x is an unsigned long, defined as a 0 up here. So I'm not cheating, that's a long. I'm going to display the x. If I show you my right number function, still at 8 megs. It's just a function without a void statement, which means it can return a number. Which when I was debugging it, and this optimizer was getting rid of half my flags and not telling me, it took me weeks and weeks to get this function working properly. So if I give you the basics, I'll start with the hundreds, just as a quickie, otherwise I will be here all night. If the number goes over 100, done to flag gets set to 0. These are all the bits looking for 100,000, 1 million to 9,999,000, 10 million. This is putting the characters in the right places so it can count. Oh, there we go. A long will only count up to 4,294,967,295. But regrettably, I've missed one of the strings off I noticed earlier. So there's my long word to string. So you saw if the number goes over 100, a flag, the done to flag, gets set to 0. This, if the number falls less than 100, and that done to flag is not 1, it clears the hundreds position. Simple. And the trouble I had developing this was these done bits were not being set and cleared because the compiler and optimizer was deleting them and not telling me. Half of this clears positions only if they have been used. So look, number string 9 is a units, number string 8, tens, number string 7, hundreds positions, and it goes on and on and on. For the length of a string, except, so this is 100 million, there should be one more string underneath for the billion, and I've forgotten it. So regrettably, this can only count up to 999,999,999. Please forgive me. Let's see, now you've seen it, I've given you the basics of how it works. Build, that's how big we are, 6,032 bytes. But, let's say for example, you only want numbers up to, let's say 10,000. You could effectively comment these out and save a couple of thousand bytes. But I am not going to comment anything out. There's no cheating. This number is capable of writing anything up to you currently, because I'm missing one set. It can today write 999,999,999. Let's see how long it takes to write an X, which you've seen is defined as a long and it's set to 0. Start debugger. This code is already available on GitHub from weeks ago, so I can't cheat. You can go and get the code yourself, put it into your own IDE and run the debug yourself and check it. So I can't lie. Why would I kid myself? Right, step over everything. Right, it's a clear screen. It's the same 128 by 128 screen. And it has to clear every pixel. Otherwise it's not a clear screen. Step over. Oh, taking a few seconds, look. Not 18, 90.12 milliseconds. So why, when I define the TFT using the MikroElektronika's TFT library, why did it take 18 seconds and nearly 400 actual time? Right, this is it. Writing through, in fact I'll leave it on the screen, so no cheating. There's all my lengthy bytes, which are much improved on the other day. there's that long right number function, and this number can be anything. I've just got it as an X and it's a long. Oh, and that's the address above. Right, here we go. Step over. Ooh, not even enough time to say cross your fingers. 10.42 milliseconds. And I thank you. And with that, I'll say again, that is the ugly truth to these IDEs and compilers sold by MikroElektronika. How can they get away with it? I thought they were the experts. They are selling us IDEs that can't put numbers down without making a mess on the screen. And when they do put a number down, they're taking their time about it. 7 times longer than my code. And I'm only a hobbyist. So what happens if a proper programmer come along and looked? He could probably make it even faster. So we have all been sold garbage. Their code must have been written by a kid off the street who had no experience. All I keep on reading is about clickboards. They're now up to 1,000 clickboards. And as I said in a video the other week that no one's watched yet, he's so proud of having 1,000 clickboards, and he's always got 250 projects for new clickboards on the go at any one time. He should take half his engineers off of those damn clickboards and sort these damn IDEs out. They're slow, full of flaws, and quite frankly, they are embarrassing. I would be embarrassed to put my name to it. I give this right number function away for nothing. I've not made one single dime, not one single halfpenny in English, and it's free, and it's 7 times faster than what you pay for. They can't say, well, they only give us like examples and you improve on it. No, that's BS. They give us TFTs and TFT functions and libraries for TFTs. Half of them don't actually work with current screens, but yeah, that's another issue. And there is no excuse. They'll probably sit there, design small clickboards, and just sing their own praises, as the CEO did in the Mauser magazine the other week. He was singing his praises, not someone else doing it for him. I'd like to get onto Mauser and get them to ask the CEO what does he think of his own compilers. Anyway, so yeah, that is the ugly, unfortunate truth. Just like all the libraries for the TFT, they're all hidden away in this IDE, buried in case someone might steal it. What? They wouldn't want to steal it because it's clearly garbage, written by a monkey or clown. Anyway, if you've got a MikroElektronika IDE stroke compiler and you're now heartbroken, give us a thumbs up or a thumbs down. I'm sort of sitting on the fence. It doesn't surprise me. Not with the stuff I've come across over the years. And it's just clickboard, clickboard, clickboard. I'm not interested in clickboards. As I said, I'd just be embarrassed to put my name to this IDE. So, please share this, pass it around, leave a comment. Thank you for watching.